So in the lectures so far, we have seen certain basics about computer architecture. I want to give you a glimpse of what lies ahead. Okay. So one of the things I'll do is to talk about the data representation, what we have considered so far and what is left out, and then about the architectures as a whole, uh, what are more sophisticated architectures, and what is their outline. Okay. So firstly, let's look at the question of going beyond integers. What is the need for that? We have talked so far about uh, working with integers or characters or bits and bytes, but you need something beyond integers. Okay. So if you look at set of numbers, so there are integers. Beyond that, there are rationals. Beyond that, there are reals. Okay. And then you also have complex. Okay. Complex is nothing but a pair of, essentially, pair of two reals. So how do you work with these numbers which are not integers? And not only that we need to deal with things like fractions. We need to work with sometimes extremely large and extremely small values, okay, which are represented by an exponent component. Okay, so for example, when you talk of large distances, you would say something like 5.9 into 10 to the power 12 meter is the distance between Pluto and Sun. Okay, so it is this ability to have a power of some base specified, which allows you to look at very large numbers. And in the other direction, if you have very small numbers, you would have a base with a negative power of with a negative power. So how do we represent such numbers? Firstly, how do we represent fractions? Okay, we'll talk of range. So there are two aspects. One is the range from very small to very large. Other is the ability to have fractions. If you were to talk of only rational number, then you can represent them by integer pairs. Okay, so if you want to represent 5 by 8, you could say that, oh, okay, I have two integers. One is the numerator, other is the denominator. Or you can think of a string, which means a sequence of characters with a decimal point also as a character. So if there is something like minus 247.09, so it will be 1, 2, 3, 4, 5, 6, 7 characters. A string of 7 characters would represent this value. You can do that in binary, where you assume a fixed position of the decimal point or binary point in this domain. Suppose you say that you want to represent the fractional part by 5 bits and the remaining bits are used for integer part. So essentially you have an implicit point here. Okay, the left to that is the integer part, right towards that is the fraction part. But that does not take care of a large range. So you need floating point numbers where the position of this point is floating. Okay, it could be anywhere and is decided by the base raised to certain power. So you have a fraction and an implicit base and an exponent or the power part. Okay, so let's understand first binary representation when fractions are involved. So for example, what does 101.11 mean? We have positive weightage for the bits on the left of the point and negative exponent for the bits on the right. So 2 raised to power 2, 2 raised to power 1, 2 raised to power 0. And for the last two bits on the right side, it's 2 minus 1 and 2 minus 2. Okay, so you could, if you sum these, you can get the equivalent decimal value of a binary fraction like this with a fixed point. You can do conversion other way around also. Suppose you're given 0.6. How do you represent that in binary? So this I have written a representation straightforward way, but what you would do is you can have repeated multiplication by 2 and keep on collecting the integer parts. So 6 multiplied by 2 is 1.2, 1 integer, 0.2 fraction. So that gives you 1 bit, the leftmost bit. Then you take the fraction, again multiplied by 2. Look at the integer part, look at the fraction part. That integer part gives you the next bit. And you can repeat this exercise. So you will get the binary representation of a decimal fraction. It may be recurring, it may be non-recurring. For example, here, if you continue like this, you will see that this 1001 pattern is going to recur. It will be repeatedly occurring. So very simply, floating point numbers with base 2 will have 3 components. There is a sign, there is a fraction part, and there is an exponent part. So the base of the exponent is 2 here. And you have binary representation of f and e, and the sign could be numerically, it could be expressed as -1 raised to power sign, where s is 1 or 0. 1 for negative sign, 0 for positive. The fraction part, or the f, is usually called mantissa or significant, and e is the exponent, which could be positive or negative. The sign which we are putting here is sign of the entire number, whether the whole number is negative or non-negative. But the exponent itself could be positive or negative. So how do we, suppose we want to represent a floating point number in certain number of bits, let's say 32 bits. So how many bits we need for S, how many for F, how many for E? How do we divide a word into these 3 parts, and how does each part get represented? So there could be many ways of doing it, and therefore there has been an effort to standardize this. So there is a standard called IEEE 754, and we will see how that standard allows numbers to be represented. So there are 2 commonly used representations here. One is single precision, where you require 32 bits, and then you have double precision. In single precision, the division of 32 bits is as follows. You have 1 bit, 8 bit, and 23 bits. Okay, you can see that these sum up to 32. The first one on the left is sign, then there are 8 bits for exponent, and f or the fraction requires remaining 23 bits. In double precision, you use 2 32-bit words or 164-bit word, and division is as follows: 1 bit for sign, 11 bits for exponent, and total 52 bits for the fraction part. So 20 bits coming from the first word, and remaining 32 entirely used for the fraction part. Okay, so this is a standard way of dividing 32 bits or 64 bits into S, E, and F. The next question is, how do you represent each of these? So for single precision numbers, we have 23 bits for the fraction part, and for double precision we have 52 bits. Okay, we assume these fraction parts to be lying in the range 1 and 2. So one least is 1.0, and the highest value or the maximum is slightly less than 2. Okay, so if you have 1 point all ones, that's the highest fraction you can have. So since this leftmost bit is always 1, we don't explicitly represent it, thereby saving a bit. So effectively, we are using, we have a 24-bit fractional part in single precision and a 53-bit fraction part in double precision. Okay, since it is assumed that it is always 1 point something, so that 1 is actually not stored, it is assumed. Is there a question?
Sir, why did we have 20 plus 32?
Out of you see that 64-bit word, I'm looking in 2 parts. One part
From
of
the storing aspect.
Yeah, so if you are storing this in 2 memory locations, each of 32 bits, then one of the words will have 32 bit, we will have 20 bits of fraction, 11 bits of exponent, and 1 bit of sign, and the second word will be entirely for the fraction. So all this put together, you can think of it as a 52-bit fraction, and with this implicit 1, it is effectively 53 bits. Okay.
Yes.
So what is the range of values for f with these many bits? In single precision, the smallest fraction value is 1 or 1 point all zeros, and the largest is 1 point all 1, which actually amounts to 2 minus 2 raised to the power minus 23. Okay, or in a more rough sense, you could say f lies between 1 and 2. It can never be 2, it's slightly less than 2. It can be 1, always more than 1. In double precision, similar way, you have fraction lying between 1 and 2 minus 2 raised to the power minus 52. So this, what I'm subtracting is the significance value of the rightmost fraction bit. So when we represent numbers in this way, always between 1 and 2, these are considered as normalized. So if you take a floating point number which is not normalized, that means the fraction part is not between 1 and 2, you can always adjust it. Okay, you can multiply the fraction part suitably so that it becomes between 1 and 2, and corresponding adjustment can be done in the exponent part. Okay, or if it is, even if it is larger, let's say you want to represent 2.3 multiplied by 2 raised to the power minus 10. Okay, 2.3 multiplied by 2 raised to the power minus 10. So now this 2.3 you can reduce to a number between 1 and 2 by dividing by 2. Okay, so it will be 1.15, and the power is now changed to 2 raised to power, what did I say, 2 raised to power 10. So now it will be 2 raised to power 11. Okay, so essentially what you can do is you can always shift the fraction part and make corresponding adjustment in the exponent part. So you shift fraction left by 1 position, you subtract 1 from the exponent and the value doesn't change, or you shift the fraction right by 1 position, you add 1 to the exponent and the value doesn't change. So now let's move our attention to E. For single precision number, we have 8 bits. Okay, and we represent the exponent part in a biased notation, taking 127 as the bias, which means whatever signed value of the exponent is, you add 127 to that. Okay, so if it is minus 4, you add 127, you get 123. So binary representation of 123 will actually represent an exponent which is minus 4. All right, so the number being shown here is 10110101, and it is basically what we wanted to have. The exponent was 54. So this is a binary representation of 54 plus 127. Okay. In double precision, again biased representation is used, and the bias in this case is 1023. So what is the range of exponent values? For single precision, it is minus 126 to 127. So with 127 as the bias, minus 126 get represented as plus 1, and 127 plus 127 gets represented as 254. Okay, so you would notice that the two extreme values we have left out. Okay, we are not considering a 0 value or 255 value. Okay, so leaving these two aside, if you take the exponent representation, subtract 127 bias, and you will get the signed value of the exponent. So that all zeros and all ones have special meaning, which I'll come to later on. For double precision, with the given bias, the range is minus 1022 to 1023. Okay. So we talked of these three part signed numbers. How about 0? So when you make all bits of F are 0, and you don't assume any explicit 1 to the left, that represents a 0 value. So it's not a normalized value, because for normalized values, the F part has to be between 1 and 2. But here we are saying that we want to represent F which is 0. And E can have any value. We choose to have all bits 0. We mean the standardizing committee has chosen representation of 0, where all F bits are 0, all E bits are 0, and the sign bit is 0, which is exactly same as the integer 0. Okay. So integer 0 and floating point 0 have exactly same representation.
Sir?
Yeah.
So here we have 1 point, we assume 1 in the left, right? Then this would also be same, 1 would also have the same representation.
No, 0 cannot have a normalized representation. A normalized representation always desires F to be between 1 and 2. But 0 means that the fraction part is 0, and you can take any arbitrary exponent. Okay. So since it is 0, it remains a not unnormalized value. So 0 is a very special case. And for convenience, we have chosen all these so that the representation of integer 0 and floating point 0 is same.
Sir, so if we have the value of E as non-zero and the value of F as 0, that represents something, because like F here will be normalized, right?
That represents a unnormalized or non-normalized number. So I'll come to that in a moment. How do you compare and test these floating point numbers? So testing for 0, negative, and positive. Floating point number is exactly same as for integers. Okay, because 0 has same representation, and positive negative is indicated by sign bit, which is in the same position as the integers. Magnitude comparison of FP number is same as, or I should say, unsigned comparison. Unsigned comparison of FP number is same as unsigned comparison of integers. The reason is that because exponent is in bias notation and is located on the left hand side. You see, if you have two numbers, one with larger exponent, two normalized number particularly, and one has larger exponent, then irrespective of the fraction part, the one with larger exponent will be larger. Okay, and since exponent is placed in more significant position, it is towards the left. If exponent is larger, then we don't even have to look at the fraction part, and you could declare which number is larger than the other. Right? If exponents are equal, signs are same, then definitely the mantissa or the f part will determine which is larger or smaller. Okay, so it turns out that testing for 0, negative, positive, unsigned comparison are same as integer. Okay, so that makes things convenient. Now, since there are limited ranges of values, you have overflow and underflow which may occur in arithmetic operations. So overflow we have understood in context of integer, but here there is an additional thing which is underflow. So let's understand the limits of the floating point values. The largest positive or negative number in single precision are plus minus 2 minus 2 minus 23. So that's the largest f part. Okay, and we take the largest exponent. So this turns out to be approximately 2 into 10 to the power 38. So that's the largest value you are able to represent in single precision. The smallest positive negative number is you take the smallest value. So we are not looking at 0 now. We are looking at smallest non-zero number, smallest magnitude other than 0 we can represent. So we take smallest f value, smallest e value, that is minus 126, and this turns out to be 2 into 10 to the power minus 38. So roughly that is the range of values. In double precision, instead of minus 23, we take minus 52 and minus 1022, and these turn out to be of the order of 10 to the power 308 and 10 to the power minus 308. So with double precision, you have fairly large range. So this works for almost all physical cases. I mean, most of the applications are manageable within these ranges. So what is underflow? Underflow is that during computation, you get a result which is smaller than this number, but not 0. Okay, it's non-zero but smaller than this, so you can't represent it, and that is considered as underflow. So if at all, you can represent that as an unnormalized number. So how do you perform floating point operations? Let's say this is one number and that's the second number. You want to add or subtract. So now you know that when you add two fractional values, you need to align the decimal point. Okay, so same thing needs to be done here. We need to look at the exponent, and if E1 is greater than E2, then we rewrite this as we rewrite the second number as a different fraction, but the exponent is made as E1. Okay, so what is this? We simply shift F2 by a certain number of position towards right, so that the exponent becomes equal to E1. Okay, F2 is nothing but F2 divided by 2 raised to power the difference of the two exponents. So this division means that you are shifting F2 right by those many positions. Now, if you wonder why are we modifying the one with the smaller exponent, why not other one? Why not shift this left and make the exponent as E2? So shifting left means that you will be throwing away possibly some bits which are more significant. But in this case, what we are doing is that we are shifting right so that the bits which are getting thrown away are least significant bits. So once that is done, you need to simply perform addition or subtraction of the fractional part, right? And the result you get may not be normalized. Okay, you could get a sum which is larger than what you can represent, or if you're subtracting two numbers which are very close to each other, you may get the difference which is smaller than what you can represent. Okay. So first, I mean, to some extent, you can actually adjust it by normalizing. Let's say that the sum was slightly more than 2. Okay, then you can shift it right and increase the exponent. Or if the difference was there and maybe it falls between 0.25 and 5, 0.25 and 0.5, then you can multiply it by 4, that is shift left by 2 position, and subtract 2 from the exponent. So some adjustment can be done, but if the result is too large or too small, you may not be able to normalize, and you have to declare overflow or underflow. The hardware structure of a floating point adder subtractor unit is something like this. So what is the central part is this big ALU. Okay, why we are calling it big is that this is the one which deals with the fractions. Okay, and then there is a small ALU which deals with the exponent, because exponents have less number of bits, fractions have more number of bits. So as we know, we need to perform addition, subtraction of fraction or adjusted fraction. But before that, we need to compare the exponents. So this ALU first looks at the two exponents, compares them, and finds the difference. The difference tells you which of the significand has to be shifted and by how much. Okay. So there is this block shown here which performs the right shift of one of the two significants. So there is a multiplexer which selects one which is to be shifted, and which one is to be shifted is selected by this control. The other one which is not to be shifted is passed on as it is. So this multiplexer and this multiplexer will act in opposite way. You know, if this selects the left one, the other one will select the right one. And then this big ALU performs addition or subtraction. And since the result also may need normalization, so there is a shift unit here which needs to do shift left or right. Okay. And accordingly, the exponent, one of the two exponent, the one which is larger, is selected here, and that may undergo some incrementing or decrementing depending upon the normalization here. After that, we do rounding off. So I'll talk of rounding off a little bit further later. But after that, you get the result. But it so turns out that after rounding, the number may become again unnormalized, and you may have to perform normalization once again. So let's illustrate these operations by a toy example where we work with 8 bits. Okay, just for illustration, this is non-standard. So suppose we keep 4 bits for fraction part, 3 bits for exponent, and 1 for the sign. The range of E is -2 to +3. So what is the bias here? Bias is bias is 3. Okay. So minus 2 exponent will be represented as minus 2 plus 3, which is plus 1. So 0, 0, 1 is the lowest exponent, which corresponds to minus 2. And 1, 1, 0 is the highest exponent. So 1, 1, 0 means 6. 6 minus 3 bias gives you 3. So that's the range of exponent. Range of f is 1.0. That means all zeros would mean 1.0 and all ones would mean 1.1111, which is actually same as 1.9375. The resolution is the last bit, okay, which is 0.0625 and whatever the exponent is. So that's the resolution. So let's take an example for subtraction. Suppose you have these two numbers. This is the sign, exponent part, fraction part. Okay. So what does this represent? There is a sign. So minus, and the fraction is 1110. So it is 1.110. The exponent is 101. So which means 2 raised to power 2. The other number is positive 1.1011, and the exponent is 100, which means 2 raised to power 1. Okay. So from exponent, I am subtracting the bias 3. So this is binary 5. 5 minus 3, I put 2. This is binary 4. 4 minus 2, 4 minus 3, exponent 1. Now these two exponents are not same, so we need to do adjustment because so normally if you were doing by paper and pencil, this basically is minus 111.10. Okay, this is 11.011, and if you were to do subtraction, you would say that this is minus 7.5, this is plus 3.375. The result would be minus 10.875. Okay, 7.5 minus this number. So this is if you were to get to our familiar domain, do it in decimal. That's the result. Now let's do it in binary itself. So we'll do it mechanically as we do in as it would be done in the hardware. We make the exponents equal. So second one is shifted right. This is shifted right. You get 1011, and the 1 is getting thrown away. So I'm showing it red. So that is in the danger zone. It gets thrown away when you try to align these. Okay, but now the exponents are same and we can perform the operation. So you do binary subtraction. All right, you'll get 10.1011. I'll leave it for you to verify. You may not be able to quickly see that, but that's what you get if you do binary subtraction. And now on the left of the decimal, you have 210, which is beyond the normalization, which is beyond the normal range. So we shift it right, and we get 1.01011. So another one is getting thrown here. Okay. And as we have shifted this right, exponent is increased by 1, so you get 2 raised to power 3. Now this means that we have exponent, the sign is 1, whole thing is negative. 2 raised to power 3 means the exponent is 110, and the fraction, we leave this implicit 1 and say that 0101 is the fraction part. So throwing this red bit away, we basically now we bring the decimal at the right position, throw away the exponent. So it is equal to 1010.1. Okay, which means minus 10.5. So you can see that the operation has been done, but because the bits were getting thrown, we have lost some precision. Okay, we haven't got exactly what we should have got because of finite number of bits we are dealing with. We get an inaccurate value. So can we do better? The values that can be represented on the number lines. So within the given bits, what we have is we can, you see, when exponent value is 1, then the least count is 0.5. When exponent value is 2, then it is 0.25, and so on. I'm sorry. This is when exponent value is -1, the least count is 0.5. When and here the least count is quarter. If you go further down, it will be 1/8 and so on. So the value we wanted to represent was 10.875, which is lying here. And the values which are actually representable in the given number of bits are these. So what we would like to do is, round it off to the nearest value. So 11 is the closer answer than 10.5. We got 10.5, but the closest value which can be represented in given number of bits is 11. So we need to do some rounding off. Let's look at another example, and I'll not step through the details, but what I want to show you is that in this case the result is 0.25, but if you follow the process and allow the bits to be thrown, then what you get is 0.5. Okay, so here situation is different. 0.5 is representable, but we got a result which is, sorry, 0.25 is also representable. Earlier the problem was that we were getting 10.875, which cannot be represented. So we have to settle for something which is close by. But here the desired answer is 0.25, which is representable, but we are getting a wrong value because of the limited number of bits we have. So can we represent 0.25? Yes, it is representable. So where is the problem? The problem is that if we are throwing bits, if we had more bits to work with, we may not have lost that. So we do this exercise again and use one additional bit here. Okay, so although in representation we have some limited number of bits, but temporarily in the hardware we can allow more bits for doing the calculation and finally pack the result into given number of bits. So if we do that, we continue all the way up to normalization, and then we retain the required number of bits, we'll get the correct answer. Okay, I'll leave it to you to verify this. So the conclusion is that although you may have 32 bits or 64 bits for representation, but internally in the arithmetic circuit, if you use more bits, then you can retain accuracy. So how do we improve precision of computation? We need to note that precision is getting lost when some bits are shifted to right of the rightmost bit and are thrown. Okay, this is happening when you are aligning the two exponents. Okay, So how many more bits we require? How many bits we lose in alignment that can potentially be recovered during normalization? So many bits are lost. I'll just give a qualitative argument here. Many bits are lost during alignment when difference in operands is large. So if two exponents differ by, let's say, 5, then you are shifting the mantissa by 5 position. So if the difference is large, you can see that the more bits are getting out of the range. On the other hand, the bits which might have been thrown but you retain in your intermediate computation, they get brought back in the normalization process when you're shifting left. Okay, so this the amount by which you need to do left shift in normalization depends on how small the fraction becomes. So when you're subtracting, when you're doing subtraction with two numbers which are of same sign and they differ in very small amount, then you get a very small difference, and that difference will have to be shifted left in order to normalize. But if you see carefully, the conditions are different, or they are sort of non-exclusive. When the difference between the operand is large, then we do a lot of right shift, and when the difference between the operands is small, then we do a lot of left shift. So we don't do both, and therefore it turns out that you can manage with only a small number of extra bits. The standard specifies 3 extra bits for internal usage. These are called guard bit, round bit, and sticky bit. G and R are simply the next 2 bits after LSB. So as you are throwing out, you may throw other bits, but the 2 which are just next to the LSB, that you retain and call them G and R bits. And S bits represent rest of the bits which are thrown away. Okay, so the bits which are beyond G and are thrown away, if any bit is non-zero, then you make S as 1. Otherwise you make S as 0 if all the bits toward right of G and R are 0. So for example, this is your fraction. There is an implicit 1, and you imagine 3 additional bits G, R, and S. So the operands you get for performing any floating point arithmetic will be having only limited number of bits. So for example, for single precision, you will get 23 bits, and with after padding this one, you have 24 bits. But for performing arithmetic, you imagine these there are to begin with they are 0, but as you shift right and do arithmetic, these may become non-zero. So with the final result, you perform rounding off as per this logic. If G and R both are 1, then you add 1 to the LSB. If G and R both are 0, if or if G is 0 and R is 1, then you don't add anything to the LSB. Okay. If G is 1 and R is 0, then you look at the S bit. So if S bit is 1, then you add 1 to LSB. If S bit is 0, then you round to the nearest even. So S equal to 0 means that you are exactly in between two representable numbers. Okay, and you can round it either way. There'll be similar amount of loss, but if you round towards the lower value or the higher value consistently, then the errors can accumulate in one direction. So just to keep it balanced, we round it to the nearest even. Okay, what that means is that if LSB is 1, which we take it as odd, then you add 1 to LSB so that now it will be even. If LSB is 0, then you leave it as it is.
Sir?
Yeah.
Sir, how did we assign S, the value to S?
So when you are shifting, let's say in the initial alignment process, you are shifting the number to the right. Okay, so bits are getting thrown away, and the last two bits which would have been thrown away are retained as G and R. But among the bits towards right of G and R, if there is any non-zero bit which is thrown away, then you make S as 1. So S is called sticky bit in the sense that as you are moving things right, moving the bits right, if there is a non-zero, it will stick there. So S bit will hold on to any non-zero value towards right of R.
Like suppose we are throwing away 5 bits, then the last 2 bits will be stored in GNR, and in the rest 4 bits, rest 3 bits, if we have 1, then S will be 1.
Yeah.
Okay.
Exactly.
Sir, in the after the rounding, you require to normalize it again, so that would make the floating point arithmetic multi-cycle, right? Because you have to reuse the circuit that was before.
You can make it multi-cycle, or you can have go through, or you can even replicate the normalization logic. Okay, so you can do it in single cycle, but if you want to save hardware, you can do it multi-cycle. The other two operations, multiply and divide, are also not difficult. So if these are two numbers, what you're doing is you are multiplying the fractions and adding the exponents. Okay, the sign will be the XOR of the two signs, exclusive OR of the two signs. Now when you multiply two fractions which are in the range 1 to 2, the product would be in the range 1 to 4, and you may need to normalize it. Okay, the division means that you divide the fraction and subtract the exponents. Sign is again the XOR of the two individual signs. When you're dividing the numbers in the range 1 to 2, the result would be in the range half to 2. Okay. Again, they may be need to normalize. So we do the division, of course, when the divisor is non-zero. Okay. We assume F2 is not 0. So the important points are floating point representation is an approximation of the real values. Floating point operations are not exact real operations. There is an approximation involved. And associativity of operations need not hold. So in integer, we always assume that a plus b plus c can be written as a plus b plus c. But here, depending upon the order in which you perform, there may be different loss, and therefore it need not be associative. Now, finally, the special bit pattern. So if exponent, so here is a table where I'm showing special representation in single precision in the left two columns, double precision in the next two columns, and the object which is being represented is shown here. So both exponent and mantissa 0 represent 0. Actually, with even if the sign was 0 or 1, it would still be 0. But we represent it as represented with 0 sign. Okay. If exponent is 0 and mantissa is non-zero, we use that to represent denormalized numbers. Okay, very small values which are below the lowest representable values, but non-zero. So up to certain range, we can represent them. All right. The normalized numbers can have any mantissa. Okay, and exponent lies in the range 1 to 254 or 1 to 2046. If you take the largest exponent value, which we said is not used for normalized number, that is used to represent infinity when Mantissa part is 0. And 255 exponent and non-zero Mantissa means it's like an error. You have something which is not part of which is neither infinity, not normalized number, not denormalized number. So this is called NaN, which stands for not a number. And a particular in a particular program, you may use it to represent something specific, but it's not a part of the standard. Okay, now these floating point operations are done by a separate piece of hardware, which is typically called a coprocessor. So coprocessor in general are extensions to the processors. They add to the capability of the processor and make the design more modular. So extend the capability of main processor and modularize the design. They could be made available as options. Okay, so if somebody, some processors are configured that you may, if you don't need floating point, you don't take and you save some money. So it makes the design modular. In some cases, it may be integral part, but potentially it makes it something which is optional. So coprocessors typically have their own registers. They are called coprocessor registers. And with that, you need to have special instruction which allow you to load and store these registers. There are also typically instructions available for movement of data between coprocessor registers and the main registers. And then you need instructions for coprocessor operations. So example of coprocessors in ARM are floating point coprocessor, vector floating point processor, Neon processor, and Intel also has its own coprocessors. Okay. So floating point processors have floating point registers, load store instruction, instruction for movement of data between FP and integer registers, and various arithmetic instruction for single precision, add, subtract, multiply, divide, and double precision, add, subtract, multiply, divide. There are also comparison instructions and instructions for conversion from floating point to integer and vice versa. So SIMD instructions, so there are SIMD coprocessor. SIMD stands for single instruction multiple data, where same operation is repeated over multiple units of data, as you do, for example, in addition of two vectors where element by element addition is done. Typically in these coprocessors, a large register is interpreted as an array of smaller registers, and hardware performs same operation on these vectors of large registers or large vectors of small registers. So for example, if you have a 128-bit register, you can think of this as a single 128-bit number, or 264-bit number, or 432-bit number, and so on. And you can perform, let's say, element by element operation on such vector. So this is something I had discussed earlier also. Okay, now this was about floating point numbers. We try to go beyond integers. In terms of architectures, what is it that we can do further? So let's look at what we have studied. We talked about simple instruction set and the architecture defined by that instruction set, and familiarize ourselves with assembly language programming to get insight into ISA or instruction set architecture. We also took the exercise of building a system. Okay. To perform arithmetic operations, we saw how ALU could be built, and around ALU we could construct a processor which executes instruction, and we dealt with the microarchitecture of how instructions could be divided into cycles. We looked at performance issues and talked about techniques to improve performance like pipelining and organizing memory in the form of a hierarchy. So the idea of cache and virtual memory were discussed. And finally, we looked at the input-output. So what we have not studied are various advanced pipelining techniques, advanced concepts in memory hierarchy design, and architecture which have higher degree of parallelism, superscalars, VLAW, vector processors, multiprocessors, GPUs, and so on. So let's have a quick glance of what these terms mean. So let's try to understand how you achieve high performance. We can do that by doing things faster. We can get high performance by doing more things at the same time. So that is idea of parallelism. Okay, doing things faster means you are running your clock faster or trying to execute instructions faster. Or we can achieve the same computation by doing less. That also makes things better. Or we remove bottlenecks. We achieve balance, trying to speed up something and not doing that speed up in other part doesn't really help. So we need to remove bottlenecks and achieve a balance. The basic expression for finding computation time of a program or a benchmark for processor, we had defined that in terms of number of instructions being executed, the average CPI, and the clock period. But what do these things depend on? Do they depend on technology, on circuit or logic design, on the architecture, compiler, OS, algorithm? So we had some discussion on that. And if you look at this sequence, the things which are higher in this order, they would affect things which are towards the right. And those which are lower in this order tend to affect things which are on the left among these. Okay. So for example, keeping everything else same, if you change the technology, you bring in, you go from let's say 20 nanometers to 10 nanometers, the transistors become smaller. So you would typically change this clock period. Okay. On the other extreme, if you look at algorithm, you replace a bad algorithm with a better algorithm. You are not dealing with clock and cycle per instruction. You would be doing same thing with less number of instruction. Okay. Compiler and OS also significantly influence the number of instruction. So compiler can generate more efficient code or less efficient code depending upon what kind of optimizations are built in. It could influence the CPI average, because if it chooses instruction, compiler chooses instruction which have lower CPI, okay, then the overall average will be better. We have seen numerical example illustrating that. In logic design or at microarchitecture level, you are not influencing the number of instructions, okay, but you play around with the way you're dividing instruction into cycles. Okay, so that influences CPI average and T clock. The architecture, what I mean here is the ISA. By choosing suitable instruction set, you influence everything. Okay. If you have complex instruction, you might reduce N, but you might end up in increasing CPI and T clock. Okay. If you choose simple and efficient instructions, you might have more N, but you would save on. You can make it execute faster in less number of cycles. So this understanding of how various domains influence these parameters is important. But now let's get back to parallelism. Let's skip this, for example. I think I have talked of this earlier. So there are parallelism of various forms. You have data parallelism, where because you need to do same operation on multiple pieces of data, you can bring in parallelism. All right, you can do those operations in parallel. Function parallelism means that you need to do many things, many functions which are independent, so you get functional parallelism. The parallelism could be fine-grained or coarse-grained. Fine-grained means that you are looking at instruction level. Can we do more instructions in parallel? Coarse-grained means that you have bigger pieces of computation which you can do in parallel. Okay. So, example of data parallel architectures are SIMD processor. So we have talked about SIMD extensions to processor, but in historically SIMD, full-fledged SIMD computers have also been built, which have multiple processing element driven by a single stream of instruction. Okay, same operation being done on multiple pieces of data by multiple processing elements. Or you have vector processors, which are basic uniprocessor. That means they don't have multiple processing elements, but they are capable of handling vector instructions. So instructions are vector instruction. You would say add array A to array B, okay, but that will be a single instruction. An example of an SIMD computer is that there is a single control unit which looks at instruction and interprets them. So P is the processing part, M is the memory part. This also handles the I/O. And then you have these processing elements with their own P and M connected through some interconnection network. And they could operate independently, do same operation as decided by CU on different data. So this was in 1960s. It was planned to be built for a large size, 64 by 4. That means 256 processing elements, but only became so complex, only 64 were built. Okay. ELIAC came from University of Illinois, so ILLI is coming from there. Another example, slight variation here. The interconnection network is between P's and M's, and the number of P's and number of M's need not be same. So this any P can access any memory through this interconnection network. So there was emphasis on SIMDs in 60s, and example I've shown you what built, but these were very expensive, very complex, and they did not address the serial fraction. In a program, there is something which is non-parallelizable. So these don't help in that part. Okay, and recalling Amdahl's law, if there is significant serial fraction, then the overall performance improvement will not be very significant. And I/O is a bottleneck. I/O is handled by a single control processor, and therefore, if there is a large input-output to be done in parallel, that was not possible in these architectures. The vector processor, on the other hand, were more comparatively less complex and gave good performance, so they got overshadowed by vector processor. In 80s, again, these were resurrected, but again, cost was still high and they did not survive. However, the basic idea is used in some modern system, particularly the GPUs or graphic processing units. Vector processors, as I mentioned, operate on vectors. So one single instruction would be saying that you add to vector, subtract to vector, and the vectors are streamed into an output of highly pipelined function units. Vector registers hold vector data. Vectors are streamed from memory into vector registers and from vector registers to memory, and there's no cache. So that interconnection between memory and these vector registers has to be having high throughput. So this is a typical architecture. You have general purpose registers, you have vector registers, and you have vector floating point units and normal, or you could say vector functional unit, I should say, not just floating point. This is a normal functional unit. The cache is used for the non-vector operations, okay, and for vector operations you directly go to the memory.
Excuse me, sir.
Yeah.
So what do we mean by vector operations? I mean, how does this vector processor differ from the normal processor which we use?
These are designed. So normally, if you were to add two vectors, you will put a loop there, okay? So in the loop, you will load the first element of two operand, perform addition, store the result. Then you load second operand of each, perform operation, store the result. So your instructions are looking at individual elements, getting them from memory, performing operation, storing the result in memory. But here you will have a single instruction which says add these two vectors. These are the sizes. So as a result, they'll be streamed into the vector registers. Vectors will be loaded. Okay, let me put it this way: that the vector addition instruction will specify two vector registers as operands, and the result will go back to the to one of the vector registers. There'll be separate instruction which will load vectors into vector registers, and the way these are organized, that as vectors are getting loaded into these registers, the loaded elements can be passed on to vector function units. So they are highly pipelined. Okay, if you had, for example, a vector addition followed by multiplication of each element, each sum element by a scalar. So this function unit could be doing addition, element by element addition, in a pipeline manner, and the results are being passed on to this function unit, which could be doing a scalar multiplication. All right. So loading, addition, multiplication, these are all done in overlapped manner, in a highly efficient manner.
So, is the dimension specified?
Yeah.
3-dimension or 4-dimension?
Dimension would be limited. For example, if a system has 64 element vector register, and you want to perform operation on bigger vector, then they will have to be broken into 64 bit. 64.
So again, we'll move it as we do now.
Yeah.
Thank you, sir.
Okay, now let's turn our attention to fine-grained functional parallelism. That fine-grained means that at instruction level. Okay, so a scalar pipeline, the kind of pipeline we have considered, gives you some fine-grained parallelism. Okay, but you could notice that in each stage there can be at most one instruction, and the limit of this is in best case, if there were no hazard, you will get CPI of 1. So CPI will be generally 1 or more. You try to bring it as close to 1 as possible. Or if you look at the reciprocal of CPI or IPC, instructions per cycle, this will be always less than or equal to 1. So to cross this boundary, to make IPC more than 1, you need to bring further parallelism. Okay, and if you are talking of instruction level parallelism, you could have multiplicity of EX units, and also make these IF and ID and other units capable of handling multiple instructions at a time. So if instructions are independent, multiple instructions can be done in parallel. So finding instruction level parallelism is important. You could do this dynamically, and that leads to an architecture which is called superscalar. Here it's done by hardware. So this is an expensive approach. You have to have hardware which checks whether instructions are dependent or independent. So there is a hardware cost to it. More power gets consumed, but you can identify groups of instructions which can be done in parallel. So normally what you do is you look at instruction window. So you may look at, for example, 8 instruction or 10 instruction or 16 instructions in the sequence. Among them, do the analysis and find out which can be taken up for parallel execution.
Sir?
Yeah.
Sir, is it the same as pipelining?
Well, in pipelining, we are looking at one instruction at a time, and we look at multiple instructions to detect hazards. So hazard detection involves dependency analysis. You are trying to find if result of one is an operand for the other one. So same thing has to be done. The analysis is same, but now you are trying to do this analysis among multiple instructions within the window.
But sir, like the resources are limited. So how can we execute so many instructions?
You need to provide more resources. You need to put in more logic. Let's say you want to look at 8 instructions and find out which can I identify 5 out of these which are not dependent on each other and I can do in parallel. Okay, so I need this capability, this hardware to do that. And if I'm able to find multiple instruction, I also need multiple execution units, multiple ALUs. Okay.
Yes, sir.
But the analysis is limited here because I can't have too much of hardware, so I need to keep hardware simple. I'll come to this point, delays and dependencies, more in a moment. The other approach is where this is done statically. It means compiler does it. Compiler can analyze the whole program, and compiler analysis does not restrict to a small window. Okay, it can analyze whole loops. It can analyze multiple basic blocks and so on. And the hardware, it will generate code in such a manner that hardware need not worry about the dependency. So if compiler puts multiple instructions in parallel, it has analyzed the dependencies, and hardware can simply execute those. Need not check that at runtime. So this is an inexpensive approach. Compiler can analyze the whole program, but compiler doesn't know where, for example, there is a cache miss happening and there is a delay involved. If you're doing analysis dynamically, you know exactly what is happening. Okay, if there is a branch somewhere, you know if branch is getting taken or not. In compiler, you will do it speculatively. You will do a prediction. So if you want to look at a long sequence in program which goes across a basic block, it means that you need to know or predict which way the branch will go. Okay, so some static prediction has to be done in order to do the analysis. Whereas in dynamic case, much more information is known. So how superscalers work basically is that multiple pipelined execution units are there for parallel execution. You fetch multiple instructions in a buffer, decode them in parallel, that's called the instruction window, and then analyze them and schedule them dynamically. Okay, so instruction could be scheduled out of order. They are there in some order in the program, but here, depending upon their independence, you can schedule them out of order. So you need to do dependency check and resource check before execution. So you may find lot of instruction which are independent, but the number of execution units may be limited. So you need to do resource check, you need to do dependency check before you start executing. And you will do dynamic speculation. You can execute instruction in anticipation. Okay. And if anticipation is wrong, then you can undo later on. You need to preserve the sequential consistency and exception processing. So when you do out of order, even the exceptions can happen out of order. Okay, the order in which exceptions occur in a program if executed sequentially may be different from the order in which execution or the order in which exceptions occur when you are going out of order. Okay, so you need to actually preserve the behavior. So what you do is that you don't update the state, because each instruction does something. Ultimately, some state updation happens. So you can do that state updation in order. You might compute the result, but don't update the result. So that final stage where state is updated is called, after that instruction retires. So you do in order retirement. The instruction level parallelism is limited in an application that is called available ILP, or available instruction level parallelism. Then there is a limitation of the hardware and software in exploiting the given ILP. So there is what is called achieved ILP, which is less than the available ILP. So there is a fundamental limitation, that is available ILP, and then there is a limitation because of the way you are trying to exploit it. So the hardware or these limitations come because of limited number of EUs, limited instruction window which you are analyzing, limited number of instructions you can issue at any given time. This requires there are sometimes false dependencies which you can eliminate by renaming the variables. Okay, so there would be some limitation on that. And as I mentioned, that you do prediction of branch and jump instruction. So that has its own imperfections. When you try to find if some load and store instructions are independent of each other, again, sometimes speculation is used. That is also imperfect. Your cache is imperfect. And because of all these limitations, you are sometimes not able to exploit the available ILP.
Sir?
Yeah.
Sir, could you repeat in order retirement once
more? In order retirement basically is that you may execute instruction in an order which is different from the original order, but you hold back the updation of the state till the end. Okay, so the updation of state means registers, memory, flags, and so on. So that is done in order. You may keep the results ready in some temporary area, but don't post the results in out of order. Okay, you order them So that final step is done in order. And also the exceptions may arise out of order, but you again hold them back and pay attention to those only in order when the instruction reaches the end.
Hold them back as in we have to store them in some registers, right?
Yeah.
Register.
So instruction level parallelism or fine-grained parallelism has its own limit. To go beyond that, you need to look at things like multi-threading. You have multiple streams of computation which can be done independently. So you can look at multi-threading over ILP data path. So basically the kind of data path which I mentioned, where you have multiple execution units like this, and you have some stages which are trying to feed these with independent instruction. So if you can derive these independent operations from multiple threads, then you have better chance of keeping your execution units more busy. I'll illustrate that in a moment. Or you have complete processors which are replicated, okay, which have their own instruction fetching, decoding unit, execution unit, and final updation unit. You can have multiple of these as multiple cores and feed multiple threads for execution for to these. So I'll come to that in a minute. But let me first go to multi-threading over ILP data path. What you need here is that each thread which you are trying to execute would need to have its own state. Okay, so you have multiple execution unit, but it has its own value which it is dealing with, values stored in some register. So you need to replicate that. Okay, so imagine that you have two sets of registers and two program counters. So these two program counters can fetch instructions from two different streams or two different threads, and the instructions which are independent coming from these two threads could be fed to multiple execution units. Okay, so you may have time when you may have situations where one thread has enough independent instruction, so the EUs can be filled with that. But if you don't, you can take up instruction from another thread. The memory is still shared, and you need the ability to switch from one thread to other thread quickly. So, yeah.
So when the memory is shared among multiple threads, then we need multiple ports also, right? For read and write in the memory.
Well, you can have first level of cache which is different.
Okay, that will have multiple cores for cache and the rest.
No, not in this case, but in multi-core case, that is how it is done. Here, the memory might prove to be bottleneck. There will be single cache, which will hold operations required for multiple threads. So here it will be shared. So let me first illustrate the basic operation here. So here, just for illustration purpose, we are taking hardware which has 4 execution units, okay, which are represented by, look at the first pattern here, first diagram, and 4 columns correspond to 4 execution units. The vertical axis is the time axis, and what this is showing is that in, let's say, in one cycle, we are considering one thread at the moment. So from that thread, we found 2 instructions which could be done in parallel. In the next cycle, only 1 instruction could be done in parallel. In the third cycle, 3 could be done, so on. And maybe at this point, there was a cache miss and need for idling through multiple cycles. And then we could continue 1 instruction done in this cycle, 2 done in this cycle, and so on. So you could see that there's room for improvement. There are a lot of underutilization here. If you look at the next one, this is coarse multi-threading, where if a thread actually gets held up in something like cache miss, it can be, you can switch to another thread. Okay, and it depending upon how much time is required to switch to another thread. You will do that only if this stalling which is happening is commensurate with that. You can have a fine-grained multi-threading where if you have ability to switch thread in every cycle, so you could keep these functional units occupied by 2 instructions of one thread, then next cycle 3 instruction of another thread. Here you're doing a 3 instruction of third thread, and so on. So different colors are representing different threads, and attempt is to draw parallel instructions from multiple threads and try to keep the execution units busy. The final diagram is showing simultaneous multi-threading. That means that in every cycle, you can pick up instructions from multiple threads. So like in the first cycle, you have 2 instructions from green thread and 2 from pink thread. In the next cycle, 1 from pink, 3 from green, and so on. So you could see that this gives you maximum ability to keep your execution units occupied and therefore getting higher performance.
These different colors indicate different instructions.
No, different colors indicate different threads from which instructions are taken.
Is there, when we have 2 different threads in one unit, what does that mean?
A horizontal row represents one cycle. Okay, so if you look at the rightmost diagram, in this cycle you are issuing 2 instructions from one thread and another 2 instructions from another thread. Okay, so you are able to mix and combine instructions coming from different threads. Of course, dependency check has to be done, and you can take up instructions which are independent. So these 2 instructions which are from one thread, they are independent among each other. But now we are looking at 2 threads. So threads are completely independent. Right here, for example, in the second cycle, you have these 3 instructions from a third thread. So among these, they have to be independent, but across threads, the independence is assured, unless you come to a point where inter-thread communication has to take place. Okay.
Yes.
So let's put together these 3 different approaches for execution. One is simple ILP or instruction level parallelism with multiple execution units. You have register file, cache memory, and main memory. They are shared. You have SMT or simultaneous multi-threading, where you have multiple execution units and multiple register files. The cache and memory are still shared. When you have multiple full-fledged cores for executing programs, you have much more replication. You have multiple EUs, multiple register files, and some upper levels of cache are independent. Okay, they are exclusive to different cores. and lower level caches and memory could be shared. So as you go from ILP to SMT to multi-core, you can see that there is more and more replication of the hardware, and if you go upwards, you have more and more sharing. Okay, so more replication also brings more flexibility in terms of parallelism. More sharing, ease of design. The sharing of memory in a hierarchical context brings another problem. So suppose you have 4 processors with their individual cache. I'm just looking at 2 levels of hierarchy right now. So caches are exclusive. They have all private caches, and there is a common shared memory. So suppose this processor has to write some information in the memory, and another one has to read that. So there is a inter-process communication which has to take place. Since there is a shared memory, they can say one can simply write and other one can simply read. So maybe it was an array where some result is being computed and put by this processor, and the array is to be read by another processor. So shared array. Because of these caches, what will happen is that this process would actually be writing into the cache first, and there may be some delay in terms of that same data getting posted in the main memory and updated. So meanwhile, if this processor needs to read same data and it tries to read it from the cache, it would read an old value which is not fully updated. Okay, so this writes into cache, this reads from cache, and there is a problem of consistency here. Okay. So what is happening is that there are multiple copies of the data in multiple caches. So this is called cache coherence problem. And the solution lies in the cache controllers following certain discipline, following certain protocol, which is called coherence protocol. And these cache controllers in some way would communicate and interact in a mutually agreed manner so that the data always remain consistent. Okay. Okay, finally, let me talk about graphic processors or GPUs, which were originally developed for accelerating graphics, and now they are getting used more and more as general purpose processors. Some of the major manufacturers are NVIDIA, AMD, and Intel. And along with these, some programming languages to support have also evolved. CUDA, for example, for NVIDIA devices, and OpenCL, which is general across all of them. These support essentially fine-grained parallelism of SIMD kind. Same operation to be done on multiple units of data. That can be done very efficiently here. So here I'm showing a typical architecture of a GPU. The particular example is NVIDIA's Kepler GK110. So you have several what is called multiprocessor SMX, and there is a typical memory hierarchy: L1 cache, L2 cache, and main memory, which is outside this particular device. What you have on the chip are memory controllers. Okay. This block here is the one which feeds multiple threads to these multiprocessing units. Within each SMX or streaming multiprocessor, you have a large number of small cores. Okay, huge number. For example, in this case, there are 192 what are called CUDA cores. Okay. As you can see that these need to be fed data concurrently from a register file which has many ports. Okay. So each row is expanded here, shown in expanded form at the bottom. You have DP is the double precision unit. These cores are single precision floating point units. There is a load store unit and some special function units. And there are multiple rows, 16 rows of what I've shown at the bottom. This is actually half of a row. So you can imagine the extent of parallelism which is supported here. Okay, so this is a quick summary of various kinds of parallel architectures which are there. And in a subsequent course, if you happen to take that in a course on advanced computer architecture, we would look at these in much more detail and try to analyze them in terms of their performance. Okay, let me stop at this. Thank you very much.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Sir?
Yeah.
Sir, I had one doubt about the assignment, sir. Here, you had said that